Let's take a look at what happens when we compress or stretch our graph horizontally. All right, this time I'm going to use the basic cosine function. So let's say that y equals the cosine of x. And recall from our previous information that we know that the cosine of 0 is 1, the cosine of pi over 2 is 0, the cosine of pi is -1. Here's 0 again, and we see our basic cosine wave. Again, it's a periodic function and looks something like this. All right, now we want to consider the graph of y equals the cosine of 2x, not 2 pi, 2x. All right, now recall from our original graph here, point of intersection with the x-axis of the graph on the positive x-axis. We know that the cosine of pi over 2 is 0. And we see that reflected in the fact that there is a 0 in the graph at pi over 2, meaning the graph crosses the x-axis there. When we consider the graph of the cosine of 2x, and I want to find, let's just say that first 0 on this positive x-axis, we know that we're looking for the place where the cosine of 2x is 0. All right, and again, we know that the cosine of pi over 2 is 0. So in this case, we're looking at the fact that 2x represents pi over 2, or is pi over 2. And when I solve this guy for x, I see that when I divide both sides by 2, I get x equals pi over 4. All right, so under this transformation where we replace x by 2x, I see that the 0, pi over 2, gets mapped to pi over 4, this position. And my graph is going to look something like this, where my first 0 occurs at pi over 4. It's going to bottom out at pi over 2, and it's going to pass through the axis again. And we're going to have a peak here at pi. So what I see is, is that I see one complete cycle of this cosine wave in the region from 0 to pi. All right. And, the process or the graph repeats itself similarly, like so. And I see that the period of this function is no longer 2 pi, but the period is pi. Algebraically, we can solve for the period by taking the constant 2 pi and dividing by the coefficient 2 that sits in front of x. 2 pi over 2 gives us pi, and that's the period of the new function. This guy still has amplitude 1. All right, just to do another example, if I consider the graph of the function y equals the cosine of 1/3 x. Okay, and again, keep in mind that my basic cosine wave looks something like this. It's going to do this. So this is the graph of y equals cosine x right here. I'll kind of draw it in with a dotted line, sort of. All right. All right, now keep in mind that this first 0 at pi over 2, remember the cosine of pi over 2 is 0. All right, so when I say the cosine of 1/3 x is 0, I know that I'm referring to 1/3 x equals pi over 2. And when I solve this guy, I see that x is going to be 3 pi over 2. All right, so if I graph this guy, I'm going to, and I'm going to do this in orange, I'm going to sketch the first 0 of my graph at 3 pi over 2. And when I do this, I see that I'm really stretching this function, right? And similarly at negative pi over 2, it's going to come through this way. All right. So hopefully you can see that this thing is being stretched horizontally. You know, this first 0 at pi over 2 is being mapped to this guy at 3 pi over 2. All right, so what's the period? Well, the period is going to be 2 pi divided by 1/3 if we use the similar method from the last example. And 2 pi divided by 1/3 is just 2 pi times 3, or 6 pi. All right, so this thing's not going to make one complete cycle until we are out here at 6 pi radians somewhere. So it's going to be way off the graph. Okay, so I see that the effect of placing a coefficient here in the argument of the cosine function, or of the trig function, has the effect of either stretching or compressing the graph in the horizontal direction. And we can, you know, we can kind of generically write the rule that says when we look at y equals cosine or sine, it doesn't matter, of kx, if k is greater than 1, I'm going to have a horizontal compression by a factor of 1 over k. And if k is between 0 and 1, I have a horizontal stretch. By a factor of, again, 1 over k.